Ok. Mouse.
Morning. We hope you had a wonderful first day yesterday. My name is Felix, and I will be your moderator for this session. Welcome to the second day of the conference, where we will continue our exciting journey through diverse STEM fields presented to you by young researchers and experienced scientists. I'm pleased to announce we will kick off with a plenary session on the topic of the value of flexibility in electrified industrial processes. Our speakers today is Matteo Romano, a renowned professor and researcher at the Polytechnic University of Milano. His work mainly focuses on process engineering and techno-economic analysis of novel processes, as well as the production of biofuels from biomass and low-carbon hydrogen. We're glad to have you here in Romania, Mr. Romano, and we hope you'll enjoy your time here to the fullest.
Thank you for your kind introduction. It is indeed nice to be here, guest of you and of the team of Professor Kalin Kormos, Anna Kormos, and Leticia Petrescu, who are collaborators where we collaborate with for a long time in European projects. So it's nice to be here. We were reminding also about a trip I did in this area some years ago around Maramuresh, Bukovina, Transylvania. It was a beautiful round trip, but I skipped Cluj except for renting the car. So it was very nice that you welcomed me with this nice weather and had the opportunity of having a good walk in the city center yesterday. So very happy to be here indeed. By the way, I could say also some nice words about, so to make you happy about the Christian Kivu, okay, who is going to win probably the Italian championship. I will not say anything good, however. Okay, so my talk is here about value flexibility in electrified industrial processes. So the summary of the presentation, let's see if I manage it. Taking all the points is first about the motivations, and then I will go across two examples, two area of research related to this topic, related to hydrogen production from biogas with electrified steam method reforming and electrified cement production. Okay, so please, no worries. So first of all, why electrifying industrial processes? First of all, because of the emissions, basically because of the of human activities, the CO2 emissions to atmosphere, the direct emissions at the top and the total emissions at the bottom. The direct emissions, as you see, about 1/4, 24% of the total CO2 emissions are associated to industrial processes. So that is the first sector in terms of CO2 emissions. If you add to the direct emissions also the indirect emissions to electricity consumption, that is today mostly produced from fossil fuel combustion, then you end up with 34% of the total emissions, so more than 1/3 of the total emissions from industry come from, of the total emissions from human activities come from industry. So there is definitely a sector where we need to act if we want to achieve net zero in 2050 or so. There are different options to decarbonize industry. Some of them, so electrification is for sure the one that is probably the one with the highest potential. It's not the only one. Another important one, especially in some sectors, is heard about it, that consists in capturing the CO2 that is generated in the process, compressing the CO2 and burying it underground. But electrification has probably higher potential if you look at the industry as a whole. And this is connected a lot with the heat that industry needs. So most of the CO2 emissions from industry are related to the heat production that is now caused by fuel combustion. Okay. When talking about electrification of the heat, so substituting fuels with electricity to generate heat for industry, it's very important to look at the temperature at which heat is needed. When you need low temperature heat, when I say low temperature means below 150 degrees, and many processes need heat below 150 degrees. Well, in that area, very likely we will see a substitution of fossil fuel with the heat pumps, which is a very efficient way to produce heat with low emissions. For the heat above 150 to 100 degrees, then we will need more expensive and more novel processes, more novel technologies based on direct electrification. And so this chart, by the way, shows the sectors that today consume more heat. And as you see, chemicals production, we are in a chemistry and chemical engineering sector. The chemicals are the most energy demanding, the one that consumes more heat at all temperature levels. So its electrification is definitely a relevant topic for this industry. You see a small part of it is low temperature heat, the yellow and the orange parts, while the reddish parts are higher temperature heat that might be electrified at some point. So what is the source of electricity that we should use when electrifying an industrial process? First of all, it must be low carbon emission, okay? If you produce electricity with fossil fuels and then electrify a process, you will end up with higher emissions overall, of course. So you need to have low emission sources. What are the low emission sources? Nuclear power is for sure one option. Renewable energies, and among the renewable energies, we can distinguish two classes. The first one is base load renewable energies, so that can produce electricity base load, so constantly all along the year, all along the day, which are, for instance, hydropower, if you have a river, or geothermal energy, okay, that are not subject to day-night cycling or seasonal cycling. And then we have the variable renewable energies, photovoltaic and wind, which are variable. It depends on the day, it depends on the season, etc. Okay, so if we had systems based on nuclear or baseload renewable energies, yeah, okay, the problem would be pretty simple to address from a techno-economic perspective, which is the area I'm in. While if we have variable renewable sources, that is becomes challenging to couple variable renewable sources with industrial processes that needs energy at constant level, baseload, because they typically run 24 hours, 7 days a week, right? Also, this makes the research more interesting because we have a problem to solve, which is not trivial. And by the way, if you look at all scenarios, these are a couple of pictures from IEA, but most of the scenarios tell us that the decarbonization of electricity production in the coming decades will happen mostly through photovoltaic and wind energy, which makes this analysis relevant. Okay, so some other important features on this regard. So first, when you in most cases becomes take the highest cost share in the production of that good. So energy has a high cost, electricity has a higher cost than a fossil fuel. So when you electrify process, the cost of electricity becomes the number one cost when you make the techno-economic analysis. So it's important to operate to reduce the cost of electricity. Second point, if we have a flexible chemical process or a flexible industrial process, we add a degree of freedom that allow us to follow a bit, at least partly, the energy that is produced from solar and wind power. Okay, so this reduces the need of electricity storage in batteries or in other with other technologies. And storing electricity is very expensive. We know that the cost of batteries is dropping, but it remains a high cost, a high way to accumulate energy. So if we can reduce the need of electricity storage devices like batteries, we should be able to source energy at a lower cost. So this is the motivation behind the flexibility. What are the price to pay when you have a flexible chemical process or a flexible industrial process? Is that you end up with a higher capital cost, because you need to oversize your equipment, because that means that you need to produce more when you have more sun and wind, and produce less when you have less sun and wind. So the capacity factor of your equipment reduces. So you need to oversize compared to the throughput, the expected maximum throughput of the process. So this is the price to pay to source energy at a lower cost. And then you need some material storage, because if you want to change the load of your chemical process, you also need to store gas or liquids. And especially for gas, it means tanks, we need compressors, which involves higher costs. Okay, so we are basically trying to find the trade-off, the optimal trade-off between capital cost and operating cost associated to investments and to electricity, or renewable electricity. Okay, so how do we, in our group, address this problem? How we have basically 3 steps. The first one, we do some process modeling with software like Aspen Plus to calculate heat and mass balances. We calculate the specifications of the equipment, we find a way to calculate the capital cost of the equipment, and we find some KPIs, techno-economic KPIs. Then, second point, we try to understand how the process operates at part load. When you have assuming that you have less electricity available, so you reduce the load of the plant. This involves still process analysis with but with different equations, because it's part load. Third, we could assess dynamics also, but we don't actually. That is a deeper analysis, type of analysis that we are not doing yet, that requires a much deeper design of the equipment. But that is definitely an option, but is important for the control of the system, which is not something that we are doing right now. The first step is to couple the industrial process and chemical process with the variable sources of renewables. Okay, and we do this by optimizing through MILP, so mixed integer linear programming techniques, the optimal mix of wind, PV technology, batteries that we might need a bit, as well as the design capacity of the chemical process that we are designing, to find the optimal solution, the minimum cost or the maximum profits that you can obtain from the plant, from the flexible plant. Okay. We can go to the case studies, and we start with the first one, which is a biogas to hydrogen with electrified reform. The process is shown here with a block diagram. I guess you all know what is steam methane reforming. Yes, so methane plus water and heat, quite a lot of heat, to produce hydrogen, carbon monoxide, and then other sub-processes to get to hydrogen. Okay, so the idea here, you know, normally in the world, hydrogen is produced with a fired tubular reforming, steam SMR reactors that consume part of the feedstock, part of the gas, to supply the heat for the reaction. The idea, we start from biogas in this case, it could be methane, but we focus on biogas here. So we have a fixed biogas flow into a saturator to add water, to add steam to it. Then we have an electrified steam meter reformer. We don't want to waste. Another reason why to electrify is because that we don't want to waste the fixed amount of biogas that is incoming into the process. So we electrify the reformer, then we have water gas shifts, and so on. And then we have CO2 separation, and then we have hydrogen purification with PSA, and we have biogenic hydrogen exiting the plant. Okay, in this plant, this in its central part where you have the electrified reforming is the most energy intensive one. So what we have here in the system, all sourced with photovoltaic, wind, batteries, and a bit of grid. We accept to have, depending on the case, between 2 and 10% maximum electricity coming from the grid, because we want to rely mostly on renewables. Okay, so biogas after conditioning comes at fixed flow rate. So this is a base load over time, fixed flow rate. Then we have a syngas generation, which consumes electricity, and we want to make it flexible. So to make this flexible, we need some storage of biogas first and some syngas storage possibly afterwards to accommodate the fluctuating behavior of this steam meter reformer. Then we have gas separation. This is also pretty energy intensive, even though not as much as the central part. And this could also, in principle, fluctuate. Then we have a hydrogen storage system to deliver base load hydrogen to a user or to a user. Okay, so this is the concept. Now, before going to the techniques, let's ask as a question. And the question is, does it make sense to produce hydrogen from biogas? Okay, so we are assessing this system, but does it really make sense? Let me make a digression, trying to make the class a bit more dynamic. Okay, I'm trying to do this experiment for the first time. Let's see if it works. The digression is this one. Then I will explain why. So we have two nice cars. Okay, we'll ask you a question, what you prefer at some point. On the left-hand side, we have an electric car, a Tesla electric car, very high technology, internal combustion engine. Okay, think about them and think about the one you like most. If you could purchase one of them, what would you like most from the point of view of general quality, speed, pleasure of driving, also environmental performances? Okay. Okay, now, in order not to influence one each other, close your eyes and raise your hand if you prefer the electric car. Close your eyes, raise it more, the best, yeah. Higher because I can't see, Okay, pretty few. Most of you prefer the conventional BMW. Okay, now, now the game would have been, I plan to say, okay, those who prefer the electric car go to the left, those who prefer the BMW go to the right. That doesn't make sense. Okay, now think about safety. Which one of you, especially related to the, for instance, the risk of fire in the batteries and the risk of fire with a petrol car? Who, again, closing your eyes, let's see, let's try. Who of you think that the electric car is safer than the petrol car? Raise your hand if you think that the electric car is safer. If you, okay, I didn't track those who, but most of you, let's say, what comes next is that most of you prefer the BMW and you also think that it is safer a BMW compared to an electric car because, for instance, the risk of fire. Okay. What we have probably seen in many cases, you might have a strong opinion, but it may be that you, as human beings like myself, are subject to so-called affect heuristics, which it's described nicely in this book. I don't know if you know it, which is by Nobel Prize in economics, Daniel Kahneman, Thinking Fast and Slow. It's a very nice book that all people involved in finance read and know very well. It's a Nobel Prize in economy, but too few people working in science read, too few. It's a very interesting book that discuss and present the biases in our mind. So, or that so-called heuristics. What are the heuristics? Are shortcuts that our minds take to following our instinct, basically. And the one I like most of these heuristics and these biases is the so-called the affect heuristics, which is, as they say, it's a heuristic, so a shortcut in which people make judgments and decisions by consulting emotions rather than logical, rational way of thinking or discourse. So this is the chapter it describes. So, by the way, I heard a video about making presentations some days ago, and they said, don't put too many words in slides. So here it is. And don't read the slide. So I'm going to read it. But just the following, the bottom lines in bold. And this really become from an experiment, okay, which is described here, that they make similar to this one. So they ask a group of people if they like a technology, and then if they perceive it as a risky. And what they found is that there was a strong correlation of perceiving as low risk the technology that we like, which doesn't make any sense because we can like a technology which might be riskier. We shouldn't see any strong correlation between these two features. And what is our mind doing is the affect heuristics in the end simplifies our lives, creating a world that is tighter, much tighter than reality. So good technologies have few costs in the imaginary world we inhabit. Bad technologies have no benefits, and decisions are easy. In real worlds, of course, we often face painful trade-offs between benefits and costs. Okay. Why this digression? This digression is because very often when we assess a technology, for instance, like biogas to hydrogen, this is the end of the digression, especially when we are not necessarily younger, I think at any age. At some point, we start loving the technology or we like the technology we are studying, which is okay. So you should like what you are studying, what you are searching, and but we might underestimate the risks, or let's say the drawbacks more in general, not just the risks, but the drawbacks of the technology. So a suggestion I have for you is, as most of you are students, so of course be passionate about your technology, about your studies, what you are doing. That's very important. But try also to zoom out to see your technology from a wider perspective and be aware of affect heuristic. Don't identify yourself with the technology, and feel free to criticize it or to have try to have a clear mind. In few words, be aware of the affect heuristics described before. This holds, of course, if you want to become a scientist. If you want to become politicians, don't care about this. If you want to become activists or politicians, yeah, you need to exploit affect heuristics in your audience. So back to the question. We spent a couple of years studying this process, biogas to hydrogen, and the question was, okay, we are spending time on it. Does it make sense? Well, If you need hydrogen in a process, for instance, in a refinery or in a biorefinery, if you want to look good, of course, it makes sense to produce hydrogen from methane, definitely. However, very few chemical processes are nearby biogas digesters and need a small hydrogen plant from biogas that generates hydrogen for a chemical process. The only real example where such a system could nicely fit is in margarine production, food industry. Okay, when you produce margarine, you need hydrogen, and it would make sense to have in the food industry a biodigester to manage the waste from food production, produces biogas, and may have reforming to produce hydrogen for margarine production. Okay, this makes sense. But if you have to use hydrogen as a decarbonized fuel, well, biogas is already a carbon neutral fuel because it has a biogenic origin. So spending money in a complex chemical process to produce biohydrogen from biomethane biogas, especially in small plants, because biodigesters are relatively small plants compared to the demand, make a little sense. Unless you capture the CO2 to produce a negative emission hydrogen. But still, the plant is small, which makes overall system hard to be competitive in real life. So this is to say, there are probably few cases in the real world where this process could fit. Nevertheless, it was a nice process to assess. And so if you are aware of it, you can still learn from studying such a process, even if you can admit this is a very niche one that in most cases will likely not make sense. Okay. End of the digression and back to the process. So this is the block diagram of the process. Again, biogas in, saturation, so to mix steam, electrified reforming, water gas sheet, CO2 separation, hydrogen purification, and so on, and hydrogen delivery. This is the block diagram. On the right-hand side, you see the process flow diagram that is closer to what we have on the Aspen Plus simulation process. So it's more complex, of course, than the block diagram. We calculate the heat and mass balances. We start with biogas with a given composition. You know, typically biogas is 50% methane, 50% CO2. The flow rate is pretty small. By the way, this is the typical flow rate that we have in Italian biodigesters, biogas plants, because we had 10, 15 years ago, we had incentives that that was given to biogas to electricity plants up to a certain size, up to 1 megawatt electricity. So this type of plants were highly incentivized in Italy until 2010, 2015. Before that, we had many plants of this size, which is the maximum size to produce 1 megawatt of electricity and get the incentives. So we got the energy balance shown here for some indicators. So it's interesting to see, for instance, the net emissions negative because we are capturing CO2, which has a biogenic origin. So it's we are basically cleaning the atmosphere. This is a sort of negative emission technology. And we have this specific electricity consumption, which is 17.7 kilowatt hour per kilogram of hydrogen. This is another nice indicator because it shows that the energy consumption is about 1/3 of the electricity consumption of an electrolyzer. Okay, water splitting. Anyway, this is the energy balance coming out from that analysis. Then the second step is the off-design analysis. Off-design analysis, so the question was, what happens if we reduce the load of the reformer? We are in a period of time where we have little wind, it's night, no sun, the battery is low, for instance. So let's operate at the minimum load, at low load, say 50% of the load. What happens? And now, of course, the equations change a bit because you have columns with the columns for CO2 absorption of a fixed size, what was designed in the previous step, you can vary, you can tune the solvent flow rate to achieve a certain CO2 separation efficiency, 95%, for instance, in this case. We can control the exit temperature from the reformer to keep the temperature at the design one. The heat exchangers should be calculated considering that they have a fixed area determined at the previous step, so the temperatures of all the plant change and need to adapt to the flow rate. So you end up with, this is the temperature heat diagram of the streams of the plant at full load and 50% load. And for example, what you need to track here is if there is some critical process, for example, the water gas shift reactor, you need to make sure that the inlet temperature at the water gas shift reactor is okay for the catalyst in the water gas shift reactor, even at part load. We checked that. That was the case with the design we had. So we say, okay, the plant looks that it can work. We see no showstopper for the plant to work at partial load. And we also can calculate the heat and mass balances of the plant at any load. Then last step is to have the system optimization. We use the GAMS in this example, which is a tool to optimize with a mixed integer linear programming system, but Python has similar libraries. It's also free, while GAMS we have to pay a license, so we are moving to Python, by the way. What should we optimize? So for a given size of a biodigester, the point to be optimized are how many photovoltaic panels should we install, how many wind turbines should we install, how many batteries should we install, what is the maximum capacity of the chemical plant, what is the capacity of a gas storage system. And then you need to have the operating variables. So what to do every hour of the year. So for every hour of the year, we need to decide what is the optimal load of the chemical plant and where energy and gas should go. If the gas should go to the reactors, or if it should go to the storage, or if you should take gas from the storage. And if the energy should be stored in the battery or used in the plant, in which part of the plant. Okay, every hour of the year, we need to take this decision based on economic optimization. Okay. So how, for example, that such a system would behave? Yeah, I don't know if you can all see, but let's say on the top of this black horizontal line, you have the production. So you see the blue part is the wind. Every bar is 1 hour of 3 days, 3 consecutive days. So the blue bar is wind, and you see it varies. Some hours you have it, some other hours you don't. The orange bars represent the solar production, and as you can imagine, only during the days. So the second day was a bit cloudy based on statistical data. So we have less sun, and of course at night we have 0 solar power. Then at the top we can also have some green bars that shows the electricity taken from the grid. So for instance, at the night between the second and third day, there is no sun and no wind. So in that period of time, we use the grid as a backup. On the bottom side, you have how the energy is used. And you see the green bars represent the load of the chemical plant. So when they are longer, you see the demand of the chemical plant of the reforming at the maximum load. When the green bar is short, you see the load of a chemical plant at the minimum load to absorb less electricity. So for example, in these 3 days, when you have a lot of sun and wind, the plant works at the maximum capacity, the reforming works at the maximum capacity. At night, with low wind, the plant works at the minimum capacity to absorb the least electricity it can. And as a result, you also see the trends of the gas storage. So when you have a lot of energy and the plant works at the maximum load, you empty the red line, the biogas storage, and you fill up the syngas storage tank, and vice versa. When you run out of energy, when you have low electricity, it's better to store biogas, so the red line goes up, and the syngas storage is emptied to supply a fixed amount of hydrogen to the user. Okay? Moreover, when you have this type of systems, when you have very high sun and wind power generated, you have to curtail some of the electricity. And this is this gray purple line, bars. This is excess electricity, which is wasted. You could sell this electricity to the grid, having some revenues, but what we assume typically is that in the future, because these sources all produce at the same time, that means they are synchronous. That means that probably also the grid will be plenty of solar and wind electricity. So the prices in the grid in those hours are going to be very low. So you will not be able to sell at any price that energy to the grid if all the grid is decarbonized in the future. So we assume that this energy is really curtailed, have no value. Okay, so this is just the example on how a system could work after optimization in 3 representative days. How about an unflexible process? What if we remove all the gas storage units and we assume that the plant works stably, taking energy every time, every hour, the same amount of energy? These are other 3 days, not the same as before, but now you see that the flexibility is in charge of the batteries. So you have these purple bars with or what actually the red bars where the battery is charged when you have a lot of wind and sun, and then the battery is discharged in the purple violet lines bars there. Okay, and you still have some curtailment, you still have all the other factors. The plant demand, as you see, is fixed, no flexibility. So the question in the end after optimization is what is better, what you gain one in the 2 cases. Very important when you do this optimization, you need to take assumptions, and the devils is in the details. So the devils is in the assumptions you take, especially the economic assumptions. So we typically have scenarios, short term, which means today cost of the technologies based on public reports, and the long-term assumptions. So how much we expect photovoltaic, wind, batteries will cost in the future, say in 10, 20 years, also taken from references. And these are the assumptions. I'm not going to discuss them, but this is the principle. Other thing very important is the location. As you can imagine, the optimal solution, the optimal indicators depend on the location because it depends on the patterns of wind and solar along the year. So we took 3 locations, 2 in Italy, north of Italy, south of Italy, and Denmark. Denmark, wind-dominated country, pretty low solar energy. South of Italy, good solar availability, also pretty good wind in some locations. In the location we took, it has good wind availability. North Italy, where, by the way, most of the biogas plants lies in Italy, because that's the agricultural area of Italy and industrial area as well. Fair amount of solar energy, but very, very low wind. We are in the least windy regions in Europe, probably, and in the world. So, yeah. And then we also assess 2 capacity. The capacity, the size of biogas plants showed before, but we also assume to have a 10 times larger biogas plants to see how the scale affects the optimal solution. So more flexibility in the end means less energy produced. That means that you need less photovoltaic and less wind power plants. You have less curtailed electricity, you have less excess electricity, and you have less capacity of storage, of battery storage. Okay, you see here for the 3 locations, North Italy, South Italy, and Denmark, the first bar is inflexible plant, the right bar is the flexible plant. So the flexible plant, you have shorter bars. In the inflexible plants, you have larger bars. You need larger bars because you need to store more energy in the batteries, these red bars, and you end up with higher curtailment compared to the flexible plant. But the price to pay, said before, so you have the better renewable energy system with a flexible process, but with a flexible process, you have also much higher capital cost, 45% more capital cost because you have to oversize all the equipment, including the steam methane reformer, the water gas sheet, the CO2 separation technology. They are all larger because they need to produce more when you have more energy. When you combine everything into an indicator of a hydrogen production cost, you have some fixed cost. One important one is the biogas cost, which is the same for everyone. You see here again, this is for the small scale plant, north of Italy, south of Italy, Denmark, in the short term. And then again, north of Italy, south of Italy, Denmark, in the long term scenario. And we see that when you have a flex, and then every couple of bars is inflexible, flexible, inflexible, flexible. Here you have a levelized cost of hydrogen production in euros per kilogram of hydrogen. Overall, when you calculate this indicator in the short term, and this is small scale, we can have hydrogen, we can produce hydrogen at 11, 14% lower cost compared to the inflexible plant. However, when we go to long-term scenario, where the batteries cost less, where the technologies for producing renewable energy cost less, then the benefit of a flexible process is much lower, minus 4%. Okay? So in this case, the value of flexibility on a hydrogen plant like this is between, say, in these locations, between 4 and 15%, depending on the scenario and on the location. And yeah, this is more or less the outcome. The total cost in the end is pretty high, say between 5 and 7 euros per kilogram in the short term, which is pretty high, but it's lower than the expected cost from electrolysis. And in the long term, it's between 3.8 and 4.4 euros per kilogram, which is still competitive with electrolysis. But of course, it's like more than 2 times costlier than current hydrogen production from fossil methane. If we go to the large scale, okay, what happens when you grow in scale? You know why industrial plants, chemical plants tend to be big plants. You tend to have few big plants rather than many small plants, because the larger, the better for the capital cost, because you have scaling function, so that the larger you are, the lower is the specific cost per unit of capacity of producing the good you are going to produce. So when you go larger, you have more benefits from a flexible process, because the price to pay in terms of capital cost of a chemical plant is lower than when you have a small plant, because you have favorable scale effects. And so we see in this scenario that the advantage, so the value of flexibility is higher when you go to larger plants, up to 22% lower cost compared to the inflexible process. So main conclusions, again, flexibility involves higher plant capex due to equipment oversizing, material storage, but so the optimal operational flexibility results from trade-off between renewable electricity cost and plant capex, and depends on the renewable technologies, the electrical energy storage. It depends on the pattern of renewable energy production. So on the location, it depends on the plant scale. Okay, so again, this conclusion referred to the specific case study we had, but it could be translated to other electrified reforming processes. The second case study, I will go shortly on this, is about electrified cement production. I don't know if you know how cement production works, but what cement plant does is basically starting from a mix of materials, calcium carbonate, silica, alumina, and iron oxides. Which is fed into the kiln where you have a fuel combustion, which heats up all these materials and form clinker, which is a mix of calcium silicates that has binding properties. Okay. What happens in this reactor, in this kiln, is that the calcium carbonates decompose, forming calcium oxide and CO2. So in the end, in a cement plant, 60% of the emissions doesn't come from the fuel that you burn, but come from the calcination reaction. Calcium carbonate decomposes into calcium oxide and CO2. So, well, then this is the real cement plant, which is a bit more complex, but we don't have time to discuss it. So another question is, again, beautiful project. We had beautiful project on this topic. We enjoyed a lot, we learned a lot, but the final question is, does it make sense in the end to electrify cement production? And my answer, at least, is just a little. Because you can avoid maximum 40% of emissions. The remaining 60%, which comes from the calcination of the material, are unavoidable. So you anyway will need for a deep decarbonization, because our target is to go to net zero. Our target is not to get to 40% emissions. It is to go to net zero. So we need to be more than electrifying. And that more, because we are managing inevitable CO2 emissions, is carbon capture and storage. So we will need, in the end, to take that CO2 and to put it underground. So if you need to do that, in the end, you can keep burning a fuel and capture the CO2 that you generate from the fuel too. And it's most likely, most economically competitive than electrifying cement production. Nevertheless, this is a nice case to apply our methods and to see what we could learn. And this is two papers that we published on this topic. The first one compared different options to electrify cement production. The second one, which has been recently accepted, assess the opportunity of flexible operation. And in few words, the idea to have this direct electrification is to have an electrified calciner, so to supply the heat for the calcination reaction shown before with an electric heating process, and then keep a rotary kiln where we burn some biogenic fuel where we capture the CO2. Okay, this is also because electrifying the rotary kiln is technologically much more complex than electrifying the calciner, which is a fixed reactor, where the rotary kiln rotates and you need a higher temperature. So it's much more complex. So we selected this process and how to make it flexible. We make it flexible by decoupling the two sections of the plant which are today coupled. And in between, we stored calcined material. So we have an electrified calcination section, a fuel-based clinker production process running base load, and in between, to manage this decoupling, we have the storage of calcined material. And storing solids is much cheaper than storing gases. So that's a nice way to store energy in the form of calcined material, calcium oxide. And everything, as before, fed by photovoltaic, wind, batteries, and a little bit of grid as a backup. Here we assessed different locations. Denmark, again, because it's the windiest and
It's a country where you have the highest penetration of wind power in Europe. We have Italy, and we have also Egypt and India, which are two regions of the world where have very high cement production nowadays. And by the way, for Egypt, it's a country that could become, like all the North Africa, could become an exporter of this time of clean goods because they have a lot of sun, a lot of wind, a lot of space. They also have much lower seasonal variability in the because they are closer to the equator. So it makes sense for these countries in North Africa to produce electrified goods, so low emission cement, low emission steel, and export to Europe. So this is a significant case. What is important when we look at these countries, also when we do the economic analysis, something that often is overlooked in academic studies is that you have, these are emerging countries that have a higher cost of capital. So high capex projects cost more because the interest rates in these countries is higher. This translates in this index weighted average cost of capital that is, for instance, 10% in Egypt and India and around 6% in Europe, which makes capital investments in Europe often more profitable. So here also you have this trade-off, better financial condition in Europe versus much higher availability of renewables and land in North Africa. So we did our analysis. Flexibility here involves, differently than before, also higher energy consumption. With the flex, so the first column is inflexible plants. The last column is a cycle of the flexible plants. And we find that we consume 11% more fuel and 6% more electricity. Why? We have this inefficiency because when we decouple the two processes shown before, you need to cool down the material and then heat it up again. So which is something that you don't need to do in the inflexible plant. So this is an additional price you have to pay, in this case, lower efficiency, lower energy efficiency. And then you have also higher capex for the cement plant, 20-25% more. Here again, these are the 4 locations: inflexible, flexible, short term, long term. That's not important. The message is you have 20-25 more expensive cement plant if you want to make it flexible, but you also see much smaller green lines, green bars when you do it flexible, because you need to install less photovoltaic, less wind, less batteries, etc. So you need less energy. And in the end, you end up with lower cost of renewable electricity. This is a correlation between all the cases we assessed, showing the levelized cost of electricity for inflexible plants correlated to the levelized cost of electricity sourced by the flexible plants. So with this system, we can source electricity at minus, so at less than 30, with saving 37 to 48% cost of the energy, which pay back the additional capital costs, as we'll see. Okay, similar patterns. What is interesting here? This shows the state of charge of the solid material. Is that when you can store materials like solids at large scale at low cost, you start seeing patterns that are not anymore daily cycling, as we saw with the gases, with the biogas to hydrogen. So you don't have a storage charging, discharging on a daily basis or few days basis, but you start having monthly or weekly or monthly storage pattern. So for instance, this is most evident in the India case, which is this pinkish line. They have a lot of sun during the summer. They store material during the summer. The electrified calcination run at the maximum load, and then they discharge the solids during the late summer, early autumn, where for some reason they have less sun. And they can store material up to 18 days. So that is the optimal capacity of the storage system. You need to store a lot of solids in the economic optimal solution. So this is also interesting. When you end up doing the cost of cement, or actually this is the cost of avoided CO2, which is sort of proxy of the cost of cement. We see that with a flexible plant, depending on the location, we save 8 to 16% of the production cost, which is good, but it's not enough to do better than conventional oxy-fuel carbon capture technology, because in the end you still need CO2 capture and storage. Okay, in most industrial processes, electrifying means getting totally rid of the CO2, which is a big advantage. In cement plants, no, you need to manage still most of the CO2 emission. So in the end, flexibility involves higher cement plant capex, higher energy consumption, but electricity is sourced at much lower cost. Locations in solar and wind resources often have higher weighted average cost of capital, so it appears better to produce elsewhere. But if you include the financing cost, the difference between Europe and non-European countries, diminishes. But an overall electrification of cement production remains hardly competitive with CO2 capture and storage. This is the end of my speech. All these type of approaches, this type of analysis, we are doing them on other cases. A nice case is iron production with hydrogen. So all systems based on hydrogen, electrolytic hydrogen, should undergo an analysis like this. This is from a project from US on e-fuels production, e-chemicals. This is e-methanol production. We had an analysis on this case, but also on bioenergy plants based on biomass gasification and production of methanol or other chemicals. Most of these funded by European projects. So, Mulțumesc. And perfect. If you're shy, you can also talk at the coffee break. If you're too shy to raise your hand. Yeah, I know. Yeah. That we think of things in this matter. Well, you mentioned the biogas and cement. Yeah. Other example, I'll go that those that I showed here. I think a very interesting case is iron production to hydrogen. There you also have a sort of competition between hydrogen to reduce iron. Yeah, it's primary steel making. So one option is to use hydrogen. It's the cleanest option, let me say, compared to using gas or coal. Well, most of the steel plants today use coal. One option is to go to gas. Another option is to go to hydrogen. Okay. What I think is that we will see more and more in the future the competition between gas and hydrogen. And what we found in our study, what I think also, is that it depends a lot on the location. You might know there is a hydrogen steel plant that is being built in north of Sweden, actually two of them. One is under construction, the other should come, based on hydrogen in the north of Sweden. So there is a high potential because they are doing that. But north of Sweden is a very peculiar situation. It's very far from the core of Europe. You have very little demand. You have a lot of hydropower. By the way, in that case, it's hydropower, so it's very stable along the day. You don't need all the storage things, and the electricity prices in the north of Sweden are always pretty low because the connection with the core of Europe is weak. It's limited by the capacity of the cables. So it's pretty. It makes sense, I think, to produce steel from hydrogen in the north of Sweden, especially if then you have a premium market which is happy to pay that steel more. While in the core of Europe, where we have a lot of demand, a lot of people, not that much land, we have many other things to decarbonize. I think that going to gas would be, and CO2 capture and storage has a higher potential. So the answer depends a lot on the location. Then we are also working on the smaller industry. I think all the small industry has a large potential. For instance, paper making, ceramic making, glass making. In this sector, also because of the scale, electrifying and then maybe trying to find a way to store maybe heat instead of electricity has a good potential because you get rid of most of the CO2 and we don't need CO2 capture and storage, which remains an expensive option and I think should be somewhat limited to large emitters like cement plants, steel plants, and maybe few power plants, chemical plants. Okay.
Next, we invite the following participants: Margarita Zakieva and Mihail Pesco, with ammonia cracking as a method for green hydrogen recovery. Please, when you hold the microphone, please hold it steady, or you can pin it to your shirt if you want.
Good morning, everyone. My name is Zakieva Margarita and my colleague. We are from Petrogas University of the Ploiești, and today we present our study, the ammonia cracking as a method for a green recovery. In the light of the current climate crisis and the goal achieving by the carbon neutrality by 2050, hydrogen is the view of key of the current careers in the future. It's important to understand that hydrogen is not a primarily natural energy source. It acts as a carrier and never finds a free form in the nature. Depending on the method, production method, the hydrogen can be classified in different types, and these classifications usually cause color classifications. The most popular and the most common type today is the gray hydrogen, which is produced by the natural gas via the steam methane reforming, and accompanying the signification carbon dioxide emissions. The blue hydrogen also is produced from the natural gas with the methane reforming, but different from the gray and blue is that the part of the resulting carbon dioxide is captured and stored. And the most and the green hydrogen is the best we can say the best hydrogen because this can be produced almost without carbon dioxide. However, it exists the different types of hydrogen, like a white, brown, and orange, but they at the moment not developed, is on the developed stage, and it's not widely adopted. The transition from the green hydrogen in Europe is not only by technology, but fairly the strict regulatory framework. Uh, the key initiatives in area include complex acts, package acts, and of legislation on the Europe units level. For example, Fit for 55 framework and Repower Europe units plan, with specific targets from the decarbonization or energy sector. In particular red directive was adopted and by the 2030 signification share of the hydrogen will be about the 42%, and the from in industry must become from the rainbow. uh, does it mean that hydrogen will be produced from the renewable source? And the 2035, this number will be grow up for the 60%. At the same time, infrastructure is being developed, and the gas and hydrogen market package, the creation of Europe network, or network operates hydrogen. It's planned and will be started on 1st January 2027. Finally, it's very important the Europe Hydrogen Bank, which they help to reduce the cost of between the gray and the green hydrogen.
Copper was processed in green ammonia. Before considering ammonia as a green hydrogen carrier, it's important to understand the process. The Haber-Bosch process is the cornerstone of the modern industry. It enables the ammonia synthesis from nitrogen and hydrogen. From a chemical standpoint, this reaction occurs under condition of chemical equilibrium. However, due to the high strength of the triple bond in nitrogen molecule, it requires stringent conditions. These conditions are selected in accordance with the Chatelier principle. Increasing the temperature shifts the equilibrium toward ammonia formation, whereas increasing the temperature. From a kinetic point of view, increasing temperature leads to an increasing rate of reaction. In practice, green hydrogen it's produced using by water electrolysis. The water electrolysis is the process where which water is broken down into hydrogen and oxygen using electricity. There are several types of electrolysis, like alkaline, PEM, or high temperature. They are the same, but they differ in operating cost, conditions, and temperature. The key point is that the green hydrogen is considered only if the electricity comes from renewable energy sources. like solar panels, wind turbines, hydroelectric powers. The the hydrogen that comes from nuclear powers is only considered orange hydrogen. Therefore, this study focuses on electrolysis uh, as the primary hydrogen source. Since green hydrogen is produced using renewable energy sources, the following challenges arises: is storage and transportation. Hydrogen has a very low density compared to ammonia, which make it difficult to transport over long distances. This is precisely why ammonia is considered one of the good hydrogen carrier. First, ammonia contains about 70.75% hydrogen biomass, with higher volumetric than compared to to gaseous hydrogen. Second, it is easier to liquefy ammonia and transport as these require less extreme conditions. In addition, there is already a well developed infrastructure from transport and storage, making it easier. Thus, ammonia provides an effective solution to the problem of transporting green hydrogen. Hydrogen can be transported in the form of ammonia and then extracted directly at the point of use. This is achieved through cracking of ammonia, which is an attractive method of hydrogen production because the reaction yields primarily hydrogen and nitrogen without formation of carbon-based products. At the same time, the literature clearly indicates that ammonia cracking is promising but not yet trivial process. Its practical feasibility depends on the choice of the economic aspects. For this reason, after considering the technical advantages of ammonia as a hydrogen carrier, it's necessary to move on evaluating operating cost uh, capital to determine the practical applicability of this.
First, we classify the ammonia cracking or the capacity range. The first category is the small, with the capacity approximately 1,500 500 kilogram for the hydrogen per day. The second category is the medium or regional level. With it's approximately 1,500 for 10,000 kilogram of hydrogen per day. And the third category is the industrial, which already grade towards centralized hydrogen for production and transportation from the 10,000 for the 500,000 kilogram hydrogen per day. The next week was this typical range classification for the cost the for cost with the minimal capital operations, cost with the minimal operation cost and the optimal balances. For the in the small range, the optimal is the system with the membrane purification. In the medium is the heat recovery with the part of energy is returned in the process. And the last in the industrial is the traditional configuration with the multiple reactors, intermediate heating, and the pressure swing at the surface. Uh, and it's very important that cost really have a it's important that uh, transport plays our important role. For example, transporting hydrogen is cost around $2 from $6 per the kilogram, when the ammonia cost around 5 cents from the $1.50 the per the kilogram equivalent.
In conclusion, we saw that ammonia is a good carrier, efficient, providing efficient storage and long distance transport of hydrogen during cracking solution. We see that cracking is not as complex as it appears, but with the with a good stuff, we can extract hydrogen and nitrogen at the base without obtaining carbon-containing products. Although it's difficult to examine the condition on cost. Like if you have a small unit, it's better to understand that we have any solution for each categories: small, medium, and large. And also ammonia is a promising pathway, but it's in implementation requires a comprehensive techno-economic approach. We want to thank you for all your attention. If you have any questions, please ask us. These are the sources of our project.
Hello, everybody. My name is Andrea Miduna Pield. I'm a third year undergraduate degree student, and today I will be presenting an Aspen Plus simulation of plastic waste pyrolysis. Okay, here is the table of contents, and we'll start off with the problem background. Okay, the global plastic crisis. Can somebody help me, please, with the... Okay, one minute, that one. Sorry for the technical problems. So for the global plastic production has reached 367 megatons per year in 2020, while on the other hand, in 1950, the global plastic production was of 2 megatons. Approximately half of the plastic produced every year is solid waste. We also know that it takes centuries for the plastic waste to be to by 2050, plastic production emission will quadruple to 6.5 gigatons of CO2 equivalent, exhausting 15% of our global carbon budget. So for these problems, our study comes with 3 main objectives. The first one is modeling the upcycling process of plastic waste at an industrial scale of 40 kilotons per year using Aspen Plus software. For the second objective, we have converting a mixture of common plastics into methane-rich and methane methane-rich gas and carbon microspheres using autogenic pressure pyrolysis. And for the third, comparing a 450 degrees Celsius versus 700 degrees Celsius pyrolysis to identify the most profitable and sustainable pathway. For our comparative analysis, we'll use the green to highlight the first scenario and the orange to highlight the second one. For the first scenario, the plastic waste will be crushed and then pyrolyzed into, which will result in three states. The liquid state will be condensed in the two-stage condensation to obtain diesel and gasoline. The solid will be disposed of, and the gas will be combusted to recover energy for the pyrolyzed process. For the second scenario, it will be also crushed, washed, pyrolyzed, and the product will result in a solid, which is carbon black, and a gas, which was natural gas. 38.9% of our natural gas that we'll obtain will be used to combust and recover energy for the pyrolyzed process. Our simulation was calculated using the Peng-Robinson thermodynamic property package, and the input feedstock was defined as a non-conventional solid. For the approximate analysis, we use it when we don't know the actual molecular weight of the plastic waste. The volatile matter was set to 1, which indicates that our feed can easily turn into gas. While on the other hand, the fixed carbon, ash, and moisture are set to 0, which means that our plastic feed is of high purity. Next. The ultimate analysis shows us that we only have carbon and hydrogen in our feed. This is primarily because plastics are hydrocarbons. And the sulfur analysis shows us that we don't have sulfur in our feed. For the particle size distribution, or PSD, we determine the work and energy for our crusher and screen to see how much is needed for the plastic to be crushed in smaller pieces. Our input feedstock composition is of 39.6 kilotons per year of plastic waste, and the components are LDPE, low density polyethylene, which is 29.23 weight percentages, high density polyethylene, which is almost 21 percentages, polypropylene, which is 32.87 percentages in weight, polystyrene, which is 11.305, and silicon dioxide, which is 5% in weight, and is also an inert impurity that is used in the plastic industry as an additive. For the simulation, we have here the technological scheme for the first scenario. In the pre-treatment part, the feed will go through a mixer, will then be crushed, and then sieved through a screen. If the particle sizes of the plastic is for the plastic waste that isn't, the particle diameter of it isn't less than 5 centimeters, it will be refed through the feed and crushed again with a new feedstock. For the pyrolysis part, we use an R-yield block as a reactor, which is set to 450 degrees Celsius and an autogenic pressure of 1 megapascals. The heat duty of it is 45.6 megawatts, and the energy consumption 3.4 megawatts. After the reaction, it will be the product will be separated with an S-split block. For the product recovery, we'll use a filter with high efficiency rate of 99.5%. After filtering the solid from the liquid, the solid residue will be mixed. And the liquid will be then filled. Will then go through a 2 condensation stage. For the first condenser, which is set to 170 degrees Celsius, we recover the diesel. And for the second condensation, we'll set it to 60 degrees Celsius to recover the gasoline. For the energy recovery part, we used an R-stoic block as a combustor, for which we set the temperature to 100 degrees Celsius and the pressure of 0.1 megapascals. The oxygen required was about 87.5 kilomoles per hour, and the input excess of air was 438.4 kilomoles per hour, and the net heat duty of it was minus 5.66 megawatts. Here are the energy recovery reactions, where through combustions go methane, propane, pentene, octane, methylcyclohexane, toluene, naphthalene, and undecine. And this was the first technological scheme for the first scenario. For the second scenario, the technological scheme will be almost probably mostly the same. For the pretreatment part, we go through the mixer, crusher, and the screens like before, but the crushed feed will go then through a washer to get rid of the impurities such as dirt and dust. After that, it will be ran through a dryer to get rid of the moisture. For the pyrolysis part, it's almost the same, but the temperature is set to 700 degrees Celsius as we said before, and the pressure is of 7 megapascals. The heat duty is the same, and the energy consumption we can see that is way lower. It's 1.26 megawatts. For the product recovery part, we use the same filter to separate the gas and solids phase. We'll collect with a mixer the solid phase to result in the carbon black. And for the gas part, we'll obtain methane, which will be then split into two fractions. The first fractions which will get out of the process is of 0.7.6%, and for the natural gas, the fraction is of 0.38, and this fraction will be then burned to recover energy in the energy recovery part. Here we can see that it's almost the same, but the net heat duty is different. It is minus 7.44 megawatts. The reactions are the same. And this was the second technological scheme for our second scenario. And here are the results validation. In our paper reference, we can see that 15.3 kilotons per year of diesel were obtained and 12.1 kilotons per year of gasoline. For our simulation, which will have the efficiency of 90%, we'll get the results of 14.7 kilotons per year of diesel and 12.03 kilotons per year of gasoline. For the second scenario, in our paper reference, they obtained 12.6 kilotons per year of methane and 17 kilotons per year of carbon black, while our simulation was almost the same, with 12.64 kilotons per year of methane and 16.92 kilotons per year of carbon black, with a small relative deviation percentage of 0.4 and 0.3 percentages. And in conclusion, Aspen Plus models were developed based on two scenarios using a common mixed plastic feedstock. The first scenario was reproduced well at the level of diesel, gasoline, annual outputs, and key product composition based on our reference. In the second scenario, was reproduced well at the level of methane and carbon black annual outputs based on the reference. The model is suitable as a basis for future sensitivity, TEA, and process optimization work, plus CO2 capture. Further work for the two scenarios, we would like to investigate the feasibility of adding carbon capture and to realize a techno-economic analysis. Here are the acknowledgements. This work was supported by a grant of the Ministry of Research, Innovation and Digitization. Here are the references. And thank you for your attention. We can go back to the slide with the I'll just say the energy recovery part was the longest that it took by defining the plastic waste as a non-conventional solid. It was harder to reproduce the exact energy that it had to take, and also the techno-economic analysis. It takes a lot of time and patience to analyze every part of it and to get with a good result to be presented. Up next, please welcome the next participant, Dorian Andrei Rus, with CFD modeling of biogas dry reforming reactor for hydrogen production.
So, hello everybody. My name is Dorian Andrei, and my presentation is CFD modeling of biogas dry reforming reactor for hydrogen production. So the presentation consists of an introduction, a process overview, model development, model validation, results, and conclusions. Now let's talk about why is hydrogen so important today. Because of our reliance on fossil fuels, we face the problem of global warming generated by the greenhouse gases emissions, especially of CO2 emissions. As we see on the graph here on the right, in 2024, the annual CO2 emissions reached almost 40 billion tons, which is a big number, and there are no signs of slowing down. So many researchers try to find alternatives for the fossil fuels, and one of them is hydrogen. So hydrogen is a good alternative for the fossil fuels because it has a higher energy yield when burned rather than hydrocarbons. And it is a zero emission fuel. It generates only water vapors when it's burned. Here there is a categorization of hydrogen depending on the methods of obtaining it and the resources used. So there are green, yellow, and pink hydrogen obtained through water electrolysis using different sources of energy, white or gold hydrogen obtained through biological production from microorganisms or natural causes. And there are turquoise, blue, gray, and black hydrogen obtained through different processes that all of them produce carbon dioxide emissions to a different degree. The worst one being the black or brown hydrogen obtained through coal gasification. Now let's talk a little bit about the dry methane reforming process. It was introduced as an alternative to the steam methane reforming by Fischer and Tropsch, and the main difference between these processes is the oxidizing agent. Dry methane reforming utilizing carbon dioxide, and steam methane reforming utilizes water vapor. So this process utilizes two greenhouse gases as reactants, methane and carbon dioxide, to produce synthesis gas at a molar ratio of 1:1 between the carbon monoxide and the hydrogen. As catalyst, it utilizes mostly metals from group 9 like cobalt or group 10 like nickel, platinum, and palladium, the most used ones being nickel and platinum. And as any other reforming process, the dry methane reforming process is often paired with a water gas shift process, as can be seen here in the scheme. We have which consists of a high temperature water gas shift reactor and a low temperature water gas shift reactor for maximizing the hydrogen production. And then we have a separation part, which consists of a condenser for separating the remaining water and a PSA unit for separating the hydrogen from the other gases. Now, there are some advantages to dry methane reforming, like it provides a use for carbon dioxide, which can motivate the implementation of further carbon capture technologies into the plants. Carbon dioxide has a low cost and it integrates well with carbon dioxide capture technology, so it further can valorify the carbon dioxide in a plant that already produces a lot of emissions. Now, the main disadvantages of the diamethane reforming technology is that the process is very endothermic. It uses a lot more energy than the steam methane reforming, and because of the high temperatures, there are a lot of, not really a lot, there are some side reactions like the reverse water gas shift or methane cracking. The last one producing solid carbon that then can form deposits on the catalyst, reducing its efficiency. So now let's talk about the model development. The model was developed utilizing COMSOL multiphysics, and there were three big steps in realizing the model. First was choosing the right geometry. For my model, I chose a cylindrical geometry because it best represents the catalyst bed or the place where the reaction takes place. Now, for reducing the resources for simulating the process and reducing the simulation time, I opted to divide my geometry into a smaller part, which can be seen here, and this is the only part that was actually simulated. Now, the second step was choosing the right modules for the simulation. I chose Darcy's law for simulating the flow through the catalyst of the gases, and at the end it will calculate the velocity gradient and the pressure drop along the reactor. Next, I chose transport of diluted species in porous media for calculating the mass balance in the reactor. As you can see, on the right side of the equation, we have the reaction term, and on the left side of the equation, we have the diffusion term and the convective term. And lastly but not least, we have the heat transport in porous media, which calculates the heat balance, where on the left side we have the convective and the conductive heat fluxes, and on the right side we have all the sources, internal or external. Yes. Now the last step was choosing the right kinetic model. For my simulation, I chose a kinetic model from the literature that takes into consideration the main reaction, which is R1, and the secondary reaction of reverse water gas shift, R2. Now, the model was developed utilizing a catalyst based on the ruthenium metal, and on the right side we can see the rate constants and the equilibrium constants for both equations. Right? Now, after developing the model, comes the validation of it. Here for the validation, I use the data from the literature from an experimental setup. On the right side of the slide, we can see the reactor from the laboratory scale. And on the left side, we have the table with all the data. After I introduced the data, I calculated the methane conversion at different temperature and compared the results with the data obtained from the literature. And as we can see, there is an increase in conversion with the increase in temperature, which is to be expected from an endothermic process. And here we see a good fit between the simulation results and experimental data. And for further another proof of that is the R-squared parameter coefficient, which is 0.9718, which shows a good correlation between my model and the experimental data obtained. Now let's talk about the results. First, I want to show you the molar profiles along the reactor for all the reactants and the products. Here I want to show mostly the effect of the secondary reaction, because if we look at the diamethane reaction, we see that at the end we should have the same molar ratio of hydrogen and carbon monoxide, but because some part of the hydrogen is consumed in the water gas shift reaction, we see that as soon as the water starts forming, the concentration, the molar fraction of hydrogen starts to decrease from the one of the carbon monoxide, which is a thing we don't want. We want to repress this reaction going on. Next are the concentration profiles along the reactor for both methane and hydrogen. Here you can see how near the inlet of the reactor, the decrease in concentration is a lot faster because the reaction rate is a lot faster here because we have the most concentration. And as we go along the reactor, reaching at like 2.5 millimeters mark, we see there is a decrease in consumption because we reach the equilibrium point and we might even have a stagnation point at the end. Same can be said for hydrogen, but here is an increase in concentration, a fast increase at the beginning and a slower one at the end until we get to the stagnation point. Next, we have the gas velocity along the reactor. Here, this graph shows how the gas flows to the catalyst. We see that we have an average velocity of 0.0 4 meters per second. And on the right side of the slide, we have the pressure drop along the reactor, which shows between the gas and the catalyst. And other things that might affect the pressure drop are properties like permeability of the catalyst, viscosity of the fluids, and even porosity. Here is the temperature profile around the reactor. On the left graph, I tried to exemplify how I use a heating source at the edge of the catalyst to provide the necessary heat for the reaction to take place. Here we can see how the heat gradient is formed. The temperature at the edge is the highest, and it gets lower as we get to the center because it is consumed in the reaction. Same can be said about the inlet and the outlet. We have a lower temperature at the inlet because here the reaction is consuming a lot more heat than it does near the outlet. Here are two sensitivity studies. First is a better look at the variance of methane conversion with the temperature. Again, here we can see how the conversion increases with increasing temperature, getting to the max value of 1033 degrees Kelvin with a conversion of 82.3%. Now somebody might ask, why are we going higher? Well, we can go even higher, obtaining higher conversions, but then we have to take into consideration the secondary reaction, mostly the ones that produce solid carbon that can lead to the deactivation of the catalyst. So here, there needs to be a lot more studies to verify if it's really worth it to go to a higher temperature than this. And the last study made is a comparison between different molar ratios of reactants in the inflow, comparing the obtained hydrogen concentration at the end. Here you can see that the molar ratio of 1:1 between the carbon dioxide and methane obtains the highest concentration of hydrogen in the end. But if we can't have a molar ratio 1:1, the next best thing we can do is to opt for a higher concentration of carbon dioxide, because if we look here, we see that it results into a higher concentration of hydrogen rather than having a higher concentration of methane in the initial flux. Now, in conclusion, a simulation of a dry methane reactor has been made using COMSOL multiphysics. The model takes into consideration the flow of gas to the catalyst, the mass transfer, and the heat transfer. Then the model has been validated utilizing data from the literature, obtaining a conversion of 82.3% at 760 degrees Celsius. And two studies were made showing how the conversion of the methane varies with the temperature, and how the concentration of hydrogen is affected by the molar ratio between the reactants in the beginning. And we obtained the highest concentration of hydrogen at a molar ratio of 1:1 and a temperature of 760 degrees. And that's Thank you for the attention. Well, I plan on further developing the model. The next step would be to really add the heat source, because here I just inputted a number that I found to be the best one. But in further developing the model, I opt to introduce a methane burning kinetic that will generate me the heat necessary for the reaction, and maybe working a little bit on the geometry of the model, implementing a more realistic one.
Thank you all for the participation and attention. Now we will have a 1-hour lunch break, followed by 4 oral presentation in the chemistry and chemical engineering section, when you are welcome to join. Thank you.
Room 97. We hope you enjoyed your meals and had a great time during this break. We will continue with the chemistry section composed of 4 oral presentations. Without further ado, I am delighted to invite Ștefan Ionel Dumitrescu to present his theoretical study on chiral boranes and their adducts with Lewis-based ligands.
Okay, may I start? Okay, so hello everyone. My name is Ștefan Dumitrescu, and I'm a student in first year of chemistry at the Faculty of Chemistry and Chemical Engineering, and I am presenting a theoretical study on chiral boranes, more specifically on tetraborane 8 and its adduct with Lewis bases. This theme, this research project is very dear to me as I have participated previously in an international chemistry tournament, which is an international competition for high school students that imagine research problems or propose eventual solutions to be done in the future. So I presented this problem in 2025 about non-carbon chiral center, or compound that is inorganic, non-polymeric, without any metal or carbon atoms that still presents chirality. And my solution back then was tetraborane 8, a very interesting compound that is butterfly-like, it's asymmetric, and I have proven by computational methods that it is chiral. So all possible topological structures converge to this C1 point group. This compound was previously reported in the literature, so it was known since the 50s and the 60s as a theoretical possibility, and they have analyzed all topological structures of this compound, like C2V, C2H, or CS point group structures, and all of them converged to a C1 structure when analyzed computationally, both back then using more primitive methods and when we used more computationally expensive methods, we still obtained this C1 structure. So this is a chiral compound, but still it is only a theoretical possibility right now, and we want to know how it can be obtained in the future. So first things first, let's prove it's chiral. I have chosen to say this compound is actually chiral. Of all types of chirality, I think actual chirality fits it most. It's obviously very difficult to study such a cluster using classical methods of chirality, but still, if you consider an axis that goes through the two central boron atoms, you can draw a Newman projection where you can see two pairs of perpendicular orthogonal groups that are asymmetric due to one hydrogen being terminal and the other three hydrogen being bridging. So therefore, this compound would be actually chiral by the International Union of Pure and Applied Chemistry definition. Moreover, it is even proven that this compound might exist, so it was observed in mass spectra in previous studies. For instance, when analyzing the pyrolysis of tetraborane 10, which is a stable and non-chiral compound, it was observed that around 200-250 degrees Celsius, this peak, molecular peak that corresponds to the tetraborane 8 formation increases. Afterwards, it decreases again. So we must conclude that it has a really narrow panel of stability, this compound. Here are some previous studies done on the pyrolysis of tetraborane 10. There are two competing reactions, the reaction that gives triboranes and the reaction that gives tetraborane 8. This study reports that tetraborane 8 is the thermodynamic product and the triborane 7 is the kinetic product. Therefore, we need to raise the temperature and prolong the time of exposure for its synthesis. Another method of synthesis that sparked my interest in this theoretical study is the synthesis of an adduct of tetraborane 10 with a ligand to obtain this adduct like tetraborane 8 carbonyl or tetraborane 8 fluorophosphine or something like that, and then decompose it to tetraborane 8. This is a better route for synthesis. Therefore, this year I have studied several possibilities and several adducts and their possible structures. As for the topology of the tetraborane 8 ligand complex family, what do we have here? There are 4 possible isomers. 2 of them are the more stable, where the ligand can be inside the basket, let's say, inside the wings of the butterfly, and that's called endo, and one where it's outside, that's called exo. There are also two less stable isomers of this compound that might be an equatorial or an axial ligand on borons that have hydride, hydride atoms that are bridging. So this is the difference, and they are in all cases found to be less stable. We have also analyzed thermochemistry, and from now on I denote the Gibbs 1 free energy for the decomposition of tetraborane 8 in the presence of a Lewis-based ligand, and tetraborane 8 ligand adduct decomposition into tetraborane 8 will be Gibbs energy 2. Okay, so therefore I have performed a theoretical study using DFT PBE0 hybrid functional with the DEF2 TZVP basis set. So this is my theory level. I have employed also an empirical correction for long range dispersion. And since in all articles it was mentioned that all syntheses that were experimentally done previously were done in gas phase, I have chosen to use standard conditioning gas phase calculations unless specifically mentioned in the thermochemistry part of my study. My presentation stopped working. So, firstly, these are the overall results. On the right-hand side of the slide, you can see the general structures of the endo and exo isomers again for reference. So, we have obtained two general types of adducts. Ones that are more stable in the endo position, generally with the smaller ligands, and ones that are more stable in the exo position, which is also less sterically impeded, as you can see, with less steric hindrance for the larger ligands and for the trimethylamine and trimethylphosphine ligands. Okay, equatorial and axial isomers, especially axial isomers, are way less stable, except for the last two compounds where the equatorial structure might be competitive with the others. These are the optimized geometries, for instance, for the tetraborane 8 carbonyl adduct. All these structures, as you can see, the endo and exo isomers are pretty close in energy, and the equatorial and axial isomers are less stable and also less symmetric. Okay, for the other compounds I have computed. I'm just presenting the most stable structure. For instance, for the D-fluorohalophosphine adducts, you can see here a trend of stability. So we might use iodine or bromine as our ligand to decompose easily or to synthesize more readily the adduct, so to decompose the tetraborane 10. But for fluorine and chlorine, we might not use them because they are not reactive at the room temperature. The tetraborane 10 won't react with those two ligands. Better ligands even are those of this structure that are fluorophosphines with different number of methylamine groups. So these ones are reacting at room temperature spontaneously. So tetraborane 10 will spontaneously react with these three ligands to form the tetraborane 8 adduct. The problem with these are that the adduct is more stable and it decomposes hardly. So we need to increase the temperature very much. So they are not optimal either. And we have also prepared some of the with 3-methylamine and 3-methylphosphine ligands that are even more reactive at room temperature and less reactive at higher temperature to decompose. So probably we have to settle in the future an exact best ligand for probably the iodine fluoride or the one of the methylamine phosphines. We have also calculated the stability of these two tetraborane 8 basket complex with ethylene that I have found in literature. It is very, very unstable and it is also just a theoretical possibility and it might not be useful in the future. As for the thermochemistry part of my experiment, I have optimized separately the structures at several temperatures in order to see where the spontaneity of these reactions become the opposite. For instance, for the first reaction, the reaction in red with the tetraborane 10 plus ligand turns into the tetraborane 8 ligand adduct, we can see that the thermochemistry diagram is not a perfect line. The reason for that is that after a certain temperature, the most stable isomer ceases to be the endoisomer and it becomes the exoisomer. So there are two competing trends that create this type of curve diagram. And by a statistical estimate at 1000 Kelvin, we will have a turn instability for the first reaction that is spontaneous. So we cannot perform the reaction above 1000 Kelvin, which is pretty obvious since it is even reactive at room temperature. While the other reaction, which is more important, the decomposition of the adduct, is not spontaneous at room temperature, it is not competing, it has no competing trends. And at 741 exact temperature, we know that the direction, the general direction of the reaction becomes inverse. So I propose this type of diagram to illustrate the stability of several adducts of tetraborane 8. So in the blue turquoise region of the diagram is the region where you can synthesize the adduct, and in the dark blue region you can see the stability window of tetraborane 8. So here we have between 741 Kelvin and 1000 Kelvin we can have a stability window to obtain the tetraborane 8, which actually would be the chiral borane. I have collected thermochemistry data on all my ligands and I will analyze them further to see how these ligands compare with each other. So which actually one of them would be the suitable one to obtain the tetraborane 8 the most easily. And also I am starting to investigate the origin of the chirality of this compound with more complex method and also start some dynamics calculation on the tetraborane 8 to see actually if there is any interconversion between the two forms that is taking place. So right now I know that I should investigate only a part of the ligands to see exactly which of them would be the most suitable for tetraborane 8 synthesis, which actually would be a synthesis of this compound that I like very much because it is chiral, non-polymeric, without any metal or carbon atoms. So thank you for your attention.
Now, Q&A session. I'm bringing that question to my
Okay, so there are some previous studies on this that propose a mechanism for a possible formation that also described it as unstable, and we have also performed some thermochemistry calculation to show it's unstable, but it has not been obtained experimentally. Okay, so I have to account for like long range stability, especially because I want to optimize the structure at every temperature possible, so not only at the baseline. So right now it's just a theoretical study, and it comes from the problem of obtaining this type of chirality without any carbon and metal atom that is not well characterized in the literature so far.
Hello everyone, my name is Stoyan Bogdan Andrei, and I will be presenting some ligands, so mono and bisulfalkenyl tetrilens that coordinate to group 10 and 11 metals. So first of all, I started from researching the literature, and I found some X-ray structures, which I took and modified some parameters. So I modified the hetero element, I modified the donor item present on the hetero element, I modified the coordination type through the phosphorus or the hetero element, and I changed the structures from mono to biphosphalkenyl. These are the skeleton of the species. On the left, we have the monophosphalkenyl tetrilens, and on the right, we have the bisphosphalkenyl tetrilens. So we have a phosphorus bonded to a carbon and to the hetero element. On the phosphorus, we have mass star, and on the hetero element, we have the donor species. The donor species used were diethyl ether and heterocyclic carbons and tetrahydrofuran. For the computational details, I used the program Gaussian 16, and I did two types of calculations. First were DFT calculations that give us the geometry optimization, vibrational analysis, and thermochemical analysis. And the second type of calculus that I did was the unrelaxed bond dissociation energies that give us the coordinate bond strength between the ligand and the metal center. And is calculating by breaking that bond and calculating the energy of the fragments. So first of all, I'm going to be starting with the group 11 metal centers. For this ligand, it only coordinates monodentate to the group 11 metals, either through the phosphorus atom or the hetero element. This goes for both mono and bisulfalkenyl tetrilens. On the right, upper right, we have a three-dimensional structure of an optimized ligand coordinated to the gold metal center. So first of all, we're analyzing which of the two structures is more stable, either through coordinating to the hetero element or coordinating through the phosphorus atom. And by that, we take the minimum of the two, and from that, we subtract the energy of the structures that we have. That's how we calculate the delta G. We have on the left the donor types. On the top, we have the types of coordination, again, phosphorus versus hetero element. And in the table, we have the three metals that the ligands coordinate to. So as you can see, for the silicon atom, always it will choose the coordinate through the silicon atom. For the germanium, though, the energies get closer, the energetical gap is closer. And in some cases, it even coordinates through the phosphorus better. And already when we have the tin complexes, the trend changes, and the more stable structure is that it's coordinated to the phosphorus atom. For the bisphosphoalkyl structures, the trends are similar, but there are some key differences. So on the silicon atom, again, the energy gap gets closer, but still the coordination to the silicon is the favored one. On the germanium, though, we have more structures that would rather coordinate to the phosphorus atom. And for the tin center, when we couple it with a strong donor ligand and bigger metal center, in this case, the coordination goes through the tin, but in the rest of the cases, it will go again through the phosphorus atom. 1 second. Now for the bond dissociation energies, we have the two tables. On the left, we have them with the donor and heterocyclic carbon, and on the right, we have the tetrahydrofuran donor. What we can see from these tables is that most of the times the hetero element metal bond is the stronger one from the two. And when we couple a stronger ligand, of course, the hetero element metal bond is going to be stronger. And another thing that we can see is that the donor ligand that's present on the hetero element center doesn't change the bond strength of the phosphorus metal coordination bond. For the bisphosphoalkyl structures, the trends are similar, but in this case, highlighted in purple, we have something different. So the metal center is going to get placed between the two phosphorus atoms, only in the case of the heterocyclic carbon, and there's going to be resonance structure that also stabilizes the phosphorus metal bond, so it keeps the metal better in there. But the trends are similar. Again, most of the times the hetero element metal coordination is stronger. So we can move on to the group 10 metals. In this case, the coordination changes. Now we have the ligand that it's going to coordinate bidentate. In the case of the monophosphalkenyl tetrilens, there's only one coordination mode, that being through the hetero element and the phosphorus atom, both at the same time to the metal. But when we have bisphosphalkenyl tetrilens, we have two coordination modes again, from the hetero element and the phosphorus to the metal and through the both phosphorus atoms. And again, on the top right, we have a three-dimensional structure of an optimized structure that's coordinated through the both phosphorus atoms to the metal. So in this case, for the bisphosphoalkyl structures, it's going to most of the times coordinate through the phosphorus and silicon, phosphorus hetero element atom. The only exception is when we couple a weak donor ligand with the tin center, and again, bigger metal. In that case, there are two structures that would rather coordinate through the phosphorus-phosphorus bond. And for the unrelaxed bond dissociation energies, on the top we have the comparison for the monophosphalkenyl tetrilens, the donors on the monophosphalkenyl tetrilens. We can see that when we have the N-heterocyclic carbon, the bond strength hetero element phosphorus to the metal is stronger than when we have a weaker ligand. And on the bottom left and bottom right, we have the tables for the bisphosphalkenyl tetrilens. And when we have a stronger ligand, we can see that the phosphorus hetero element bonding to the metal is always favorable. The bond is always favorable than the phosphorus-phosphorus bond. And when we have a weaker ligand, there's cases like in the tin and platinum complex, where the phosphorus metal bond is stronger than the heteroelement metal bond. Another thing that we can note from these tables is that when we have two substituents of phosphocalcinyl on the heteroelement, the coordination energy of heteroelement phosphorus to the metal gets higher. So we can look at, for example, the stanium or the tin and platinum complexes. When you have two phosphocalcinyl substituents on the heteroelement, the energy jumps from 110 kilocalories to 130 kilocalories. The same goes for when we have a weaker donor ligand. So what are the conclusions? Well, these complexes are heavily influenced by several factors, that being the heteroelement, the donor, the metal center, and the structures, that being mono or bisulfonylic structures. And the most important two conclusions that I want to state is that the heteroelement metal bond gets weaker in the series of silicon, germanium, and tin, while the phosphorus metal bond doesn't really change that much. And if we use group 10 metals, most of the times we will have complexes with heteroelement metal bonds, whilst if we use group 11 metals, the complexes may favor the phosphorus metal bond, especially when a weak ligand is used. And that's all. Thank you for your attention. And I would also like to thank the World Federation of Scientists for the financial support that they provided via a research grant.
For your presentation. Is there anything that you want to do in your research that you have time to, or what would be
Well, as you can see on this slide, we have another group of metals that I'm going to try. That is an iron atom in the center, and in this case, the coordination can go through all the centers that have a pair of electrons, that being the both phosphorus atom and the heteroelement. So it's going to create this. It's very interesting looking tridentate, basically coordination from the ligand to the metal center. And I'm going to check this series out too next.
Thank you all for your interest and congratulations, Bogdan, on your work. Now, I would like to ask Horatiu Casian to present his work on the computational study of diniobadicarborane and ditantalidcarborane, bear with me for this, clusters having from 8 to 12 verticals.
Hello there, my name is Horatiu Casian, and today I will present the results for my master dissertation with a topic involving the computational study of diniobide ditantalidcarboranes. The original chemistry of the polyhedra borane and carborane, in which the vertices were as similar as possible and were formed of only boron, carbon, and or the first row elements, was based on so-called closo-deltahedra. Those polyhedra had vertices that are as similar as possible, meaning they were of degree 4 and 5, with the only exception being this 11 vertex structure that is topologically required to have a degree 6 vertex. In this case, a degree of a vertex represents the number of edges meeting at that specific vertex, and most of the original metalloboranes and metallocarboranes had geometry based on this closo-deltahedra. However, after the synthesis of iron derivatives and further metalloborane research, new geometry was recognized as so-called isocloso geometry, in which there is at least one degree 6 vertex, and that is less spherical than its closo counterparts. The next step in this chemistry was the discovery of the D-RENA boranes by Gauss, Fellner, and their co-workers, who, using X-ray crystallography, found an flattened ellipsoidal oblate structure, which was later recognized as oblato-Closov structures, which has the metal atoms occupy at degree 6 or degree 7 low energy curvature points, and being bridged by degree 4 and 5 high energy points. And many of those clusters have been studied here at the molecular modeling lab at the university. And for my bachelor dissertation, I performed a computational study or potential energy study of d vanadium dicarborane structures using density functional theory. These structures were found to prefer higher spin states, such as the triplet and quintet spin states, and had a structure based on the n-1 deltahedra, with one of the faces being kept by a cyclopentadienyl vanadium moiety that has most of the density bearing on that vanadium atom. For the 8 and 9 lowest energy structures, the geometry is based on a pentagonal bipyramid, while the lowest 10 vertex energy structure has a geometry based on the Closso 10 on the Closso 9 vertex structure with the face capped by a cyclopentadienyl vanadium unit. The 11th vertex lowest energy structure has a geometry based on a bicap square antiprism, and the 12 lowest energy structure has a geometry based on the 11 Closso tetrahedral structure with one of the faces capped by a cyclopentadienyl vanadium unit. A common feature in all of those structure is the presence of the capping unit and the preference for higher spin states, which leads to the central question for my master's research, which is how does the ligand field strength affect the geometry and the spin state of the clusters when moving from vanadium to niobium and then to tantalum? We expect due to more pronounced splittings in those 5th and 6th row period metals to prefer